This lecture, we're going to start speaking about smooth analysis in earnest. So let me just sort of remind you the salient points of smooth analysis that I told you about last time. So this is an example of a hybrid model where you're trying to take aspects of average case analysis, aspects of worst case analysis, and hopefully get the best of both worlds. From average case, you're hoping to be able to make really strong and meaningful performance guarantees. And from the worst case, you're looking for things which are robust guarantees, so not overly tailored to some specific distribution. And smooth analysis is one particular hybrid model. We'll be looking at some others. And the way we described it is that there's an adversary, so this is the worst case aspect, picks some initial input. Okay, so you have some algorithm you're going to use, and an adversary picks intuitively the worst input for the algorithm that you're using. But then nature sort of saves the day. So nature adds a perturbation. So add some randomness to the input. Okay, so it's sort of worst case over the starting point, and then average case over this ideally small perturbation that nature adds. Okay, so as the perturbation gets smaller and smaller and smaller, we're becoming worst case analysis. As it gets bigger and bigger and bigger, we're basically doing average case analysis. Okay, so the size of the perturbation interpolates between those two models. So when is smooth analysis generally useful? So it's generally useful when the worst cases for an algorithm seem really brittle, like they're going to be destroyed by a perturbation. Now, these bad examples are all really complicated, so you won't actually see one in lecture. It would take too much time, but the smooth analysis examples, what we're doing, they do have that feature. Okay, so the Clay-Minty cube for simplex, if you sort of see it, you see it's sort of a nice knife's edge example. Also for local search, which we'll talk about today, there are bad examples in theory, but they're very brittle. It's just clear that they would be fragile and break down under a perturbation. Now, of the various cost measures for algorithms we're looking at, it seems like running time is usually the measure which has these very non-robust pathological inputs. So that's where we see the killer applications for the most part. Still to this day, the original application is the most famous one, the simplex method for linear programming. We talked about that a bit on Wednesday from 30,000 feet. That's all I'm going to say about it in class. The references on the website have more if you want to delve in more deeply. But today I want to give you a self-contained account of another genre of problems that are right in the wheelhouse of smooth analysis, namely local search. Okay? And one feature of discussing local search a little bit is, like, while smooth analysis has had some really nice successes in this space, in my opinion, there's still some really juicy open questions, which just someone has got to solve. So we'll talk a little bit about those at the end of the lecture. So just to remind you, so local search at a high level. So what you do is you have an optimization problem, you maintain a feasible solution, you have a notion of local moves that are permitted at each step, and you keep iteratively locally improving the solution until you can't do so anymore. And then it halts at some locally optimal solution. Okay, so that's local search in general. I'll give you a specific example in a second. So why is local search crying out for a smooth analysis? Well, so it turns out local search algorithms often do suffer, at least in theory, from pathological inputs. Okay, so they're often exponential worst case, by which I mean from a worst case starting point, you might have to do an exponential number of improving moves before you stop at a locally optimal solution. On the other hand, you run these in practice and you never, ever, ever see these exponential examples. Okay? So, it depends on the problem some, but think, quadratic or even a little bit better running time typically observed in practice. Okay? So this combination is the first thing that makes you wonder about smooth analysis. And then if you actually inspected the bad examples and saw how brittle they were, you'd really start thinking you want to do a smooth analysis. Okay? So those are sort of the clues that that's the right analysis model to be using to reason about local search algorithms and their convergence time. Okay, so that's local search just totally generically. We're going to do a case study for a fundamental problem that hopefully you all have heard of at some point in your life, the traveling salesman problem, or TSP. And we'll be looking at a special case of the traveling salesman problem. where the city, so the story is, right, so you have a traveling salesperson and they have a bunch of stops they need to make. It doesn't matter what order they make them in, they just have to go to each place exactly once, okay? And so the places, we're going to assume the salesperson has to go are points in the plane. And moreover, we're going to, for simplicity, be using the L1 metric, okay, to measure distance between two different points in the plane. And a lot of that sort of for simplicity, to keep the lecture simple. So that's what we'll be thinking about. More general results are certainly possible. So input endpoints in the plane. Actually, let's even say in the unit square. Which is almost the same thing. Okay, so we're given endpoints in the unit square. And the goal is to compute a tour. Okay, so a path that closes back on itself that visits each point exactly once. So P1, so really an ordering of the endpoints that minimizes the total distance traveled. So remember each PI, this is just the next coordinate and the y coordinate, and then distance between consecutive stops. We're going to use the L1 norm. Same L1 norm that we talked about when we were doing compressive sensing, right? So just the sum of the absolute values of the, in this case, only two coordinates. Also known as Manhattan distance in this context sometimes, right? Because sort of Manhattan, it's like the number of blocks you have to go total, going both east-west and north-south. Okay. And so similar results are possible for other norms. This is mostly for pedagogical reasons. I'm just going to stick with the L1 norm. Okay. So you probably know that the traveling salesman problem in general is NP complete or NP hard. Even this special case is NP hard. So if you don't want to work really hard and solve it exactly, then instead one considers heuristics. There is what's called a PTAS, or a polynomial time approximation scheme, for this special case. So for any epsilon greater than 0, there is a polynomial time algorithm that guarantees you a tour within 1 plus epsilon times the minimum possible. However, it's very slow. It's really just kind of a theoretically interesting algorithm. So that's not how people solve it in practice. If people don't solve it exactly, then instead they use heuristics. Local search, for 50 years has been one of the main heuristics used to generate approximate solutions to TSP instances. Okay, so that's what we want to talk about today. All right. So this will be the problem for the whole lecture. Clear? Okay. Now, when you talk about local search, right, so abstractly in each iteration you make a local move which is improving. So local search is only defined with respect to some notion of what are the local moves permitted. Okay, so you have to define the neighborhood of each feasible solution. So there's many ways to do that, including for the TSP problem. But we're going to look at a very simple and well-known and old way of doing this called the 2-op neighborhood. And so this is nice. So you maintain a tour at every step. You start with some arbitrary tour. Like initially you just go through the points in order of name, say. And in a generic iteration, if you look at two edges in the current tour, okay, so maybe at some point you go straight from U to V and straight from X to Y, and the rest of the tour is whatever it is. What you're allowed to do is you're allowed to cut these two links, okay, and rewire. Now, if you think about it, there's a couple ways to rewire this, but if you rewire U to X and V to Y, then you've taken your one cycle and turned it into two cycles, right? So you don't want that. That's not a tour. So that leaves, the interesting thing to do is to connect V to X and U to Y. The rest of the tour, by definition, stays exactly the same. Okay? So that's a 2-op move. You have your current tour. It has n edges. You rip out two of them. There's a unique way to rewire them that gives you a distinct tour from what you started with. That's a local move. Okay? So you have flexibility. because you can choose these two edges however you want from the current tour to break it up. But that's the set of local moves available. Okay. All right, and so then the algorithm that we're going to be interested in is just generic local search under this neighborhood, with the 2-up neighborhood. So you just execute, so you never do anything stupid that makes things worse. Okay, so if you sort of in your mind think about doing this rewiring and you notice it takes you longer, you never do that. If there's many different swaps that make you better, we're just thinking that you pick one arbitrarily. Okay, so if there's some improving move, then you do it. Okay, so execute improving local moves until you can't anymore. So till none remain. Okay. So by definition, the length of the tour will be strictly decreasing with the number of iterations. Okay. If you think about it, that also means that this must eventually terminate. Right? There's only an n factorial number of different ways, actually less than that by symmetry, that you could go through all of the points. That's a finite number, so eventually you'll run through all of the cases. And because it's strictly decreasing, you can't cycle. Okay. All right. Now, n factorial is a lot, of course. You'd hope that you'd find a locally optimal solution much faster than that. I should also note that a given iteration, it's not hard to implement in polynomial time. Okay? So for example, n cubed is super easy, because there's only kind of n squared different edges to try ripping out, and then in linear time you can compute the result of the new tour, and you just take the best one. Okay, so there's only polynomially many options, so it's easy to execute one iteration in polynomial time. Really the question is how many iterations are required, and n factorial is not such a great upper bound. Okay? All right, so what I'm going to talk about today is drawn from a paper of Englert, Roglin, and Vocking. And there's a bunch of results in this paper. We're just going to focus on one of them. Let me actually state two of them for context. So the first thing Englert et al. Prove is that indeed, even in the special case of endpoints in the plane with the L1 metric, and even for this particular 2-op neighborhood, local search can, in the worst case, require an exponential number of iterations before halting at a locally minimum tour. Okay, so exponential in worst case. This we're not going to prove. Okay, this is sort of a very, like I said, this is a very knife's edge construction. Okay, so it's a tour de force. It's very impressive when you read it, and but I'm not sure if we went over it. I'm not sure what I'd teach you other than the fact that this is true. Okay, knowing that this is true is nice. Okay, but going through the proof again, if you're interested, just check out the paper. Okay, it's an impressive construction. What I do want to talk about is the positive result, which is that on the other hand, nature really does save the day, perturbation really does save the day, which is that local search under the 2-op neighborhood has polynomial smooth complexity. Okay? So even if you start from one of these exponential worst case examples, you perturb it slightly, local search runs fast. So recall from Wednesday that what it means to have polynomial smooth complexity is your running time is polynomial not just in the input size n, but also in 1 over sigma, where sigma is the parameter controlling the size of the perturbation. Okay, so like for a Gaussian, that was like the standard deviation. All right. Of course, there needs to be some dependence on the size of the perturbation, because as the perturbation goes to 0, we know the running time might go up to exponential. Okay, so polynomial in 1 over the perturbation size is what we're looking for. All right, so that's what I want to prove to you in this lecture.
Is this algorithm, is it optimal? Does it,
in what sense?
Does it give you the right answer? Give you the optimal answer?
Certainly not. Certainly not. It's NP hard, so that would be surprising. So yeah, I'll discuss a little bit more about the. Let me just say it now, actually. So there's a couple of disconnects between the theory and the practice of local search. One is with respect to the running time, and that's the one that we're addressing in this lecture, and that's the one that smooth analysis is appropriate for. That disconnect is between just the number of iterations observed when you run it, the difference between exponential in the worst case and subquadratic in practice. Okay? And so we're not going to get subquadratic, but we'll at least get polynomial, and so we get a lot closer to explaining what the real performance of local search is. The other disconnect is real, but I think it's a little less embarrassing for a couple reasons, but it's also harder to close. It's also hard to know how to actually close that gap, which is the extent to which the local minima, okay, which is where a local search algorithm is going to stop. It's not necessarily, I mean, if it gets lucky and reaches a globally minimum TOR, of course it will stop, because there's no way to improve it. But certainly, and maybe I'll put an example on the homework, you can have TORs which are locally optimal, say for the 2-up neighborhood, meaning any one of these swaps will only make you worse off. But if you could somehow do a much more complicated switch around of the points, you would get a better TOR. Okay, so simplex is very unusual, and that simplex for linear programming is sort of doing local optimization each time, but because everything's linear and convex, it turns out the only local minima are the global minima. For discrete optimization problems, especially NP-hard ones, but even most ones, it's not the case that local minima generally coincide with global minima. They're almost always different. There's usually many more local minima than there are global minima. So you might get stuck at something which is suboptimal. Okay? Of course, for an NP-hard problem and a simple algorithm, we're not surprised, right? We kind of always expect that if we don't work very hard for a heuristic for an NP-hard problem. So you can ask the question, like we've asked at other points in this class, can you say anything about how close to an optimal solution is the locally optimal solution that you reach? Depends on the problem. For some problems you can say reasonably interesting things. For the traveling salesman problem, in theory, you don't do so well. Okay? So the local minima, in the worst case, can be very far from global minima, even in quite simple TSP instances.
Arbitrarily far?
Depends on the assumptions. So under the assumptions for today, you can prove some kinds of bounds. So you can prove some constant bound, sufficiently big bound, where the constant also depends on the perturbation size. But the constant bound, again, is very far from what you'd observe in practice, right? So maybe this would prove a factor of 5, and in practice it would normally be 10% or something like this. So it's not that you can't prove anything, but there's a big gap between what's true in the worst case and what's observed for the empirical performance of local minima, of local search algorithms. Now, here's a couple reasons why, okay, so there's 2 reasons I think why it's a little less embarrassing, this gap between theory and practice. One is the gap isn't quite so ridiculous. Okay, it's still a big gap, but it's not as big as this, 2 to the n versus less than n squared gap. The second reason is that, if you talk about empirical performance of local search, when you talk about number of iterations, there'll be people who do local search for a living and go to the grave without ever seeing this happen once in their lifetime. I mean, this is really, really rare. But if you run local search algorithms enough, you'll definitely see some cases where they terminate at a really stupid locally optimal solution. I mean, it's not super common, but let's say 1% of the time for concreteness, you're going to see really crappy outputs. So it can happen, right? So the theory is talking about something which does sort of exist, even in the real world. Now, the main reason it's so hard to close the gap between the theory and the practice, okay, so anyone who runs local search, what you do is you don't just run it once and go to the bank, right? You run it these things take, they often take like 10 seconds to run. So run it 100 times with random starting points, okay, and take the best one. And then you're usually going to be reasonably fine, okay? So the question then is sort of how to turn that into a theorem. Like you want to say the best of 100 runs of local search with random starting points is pretty good. Okay, and that's a little intimidating actually, because there can be a huge number of local minima. There can be an exponential number of them. It's very hard to understand sort of what the structure is. If you take a uniform distribution over starting points, no one has any understanding of what the distribution looks like over the local minima you might reach. So to prove a theorem which somehow says on average over the local minima, whatever that means, then you're doing close to optimal. Don't get me wrong, if anyone formulated and proved such a theorem, it would be fantastic. Okay, but it's challenging. Okay, it would be a great, great result. Okay, so it's sort of the gauntlet's sort of been thrown there. So I'd say, so the 2 good news is the gap isn't as big as far as solution quality. Plus, I think we should feel it doesn't really feel like we're just lacking imagination in our analysis frameworks. It really kind of feels like, it does well in practice for sort of complicated, messy reasons, and it doesn't surprise me that it's eluded all of our theoretical frameworks so far. That's kind of my opinion. Okay, so end of digression. Rest of the lecture, running time only. Okay, we're going to punt on solution quality. At least let's get good running time bounds. So actually, what I want to do first is I want to reformulate the perturbation model a little bit in a nice way. So this is going to be actually a very nice notion of smooth inputs. So previously, we were talking about it like an adversary goes first and then nature perturbs it. We're going to actually smush those two steps into one, okay? So the adversary is not going to pick a single input. We're going to force the adversary to pick distributions, okay? And then there's not going to be any nature, okay? Now you should ask, well, but what prevents the adversary from picking a distribution, which is a point mass, on a worst case input? Well, what's going to prevent it is we don't let it, okay? We're going to insist that the distributions can't be too spiky, okay? They have to be sufficiently diffuse, okay? So adversary picks not too spiky density functions on the unit square with the understanding that the point Pi is going to be drawn from Fi. Okay, different points being drawn independently. And right, so on unit square. And what do I mean by not too spiky? So what I mean is that if you look at the density of any of these densities at any point in the square, this is bounded above by 1 over sigma. Okay? So it's an upper bound on the density.
What's sigma?
Sigma is a parameter. Okay, so sigma is measuring the size of the perturbation. So as sigma goes to 0, this upper bound becomes trivial, which allows the adversary to just deterministically pick a point. Okay? Now, so as sigma goes the other direction, we approach average case analysis intuitively. And if you think about it, okay, so sigma is not going to go any lower than, it's not going to get any bigger, excuse me, than 1. Okay? The only way this could be 1 is if Fi is the uniform distribution on the square. Okay? More generally, what this does, and this is maybe a way I encourage you to think about this, is this forces the support of a density, Fi, to have area, just in the usual, Lebesgue measure sense, at least sigma. Okay? And this will hold with equality if and only if this density is, if only if the distribution is uniform over its support. Okay, so if you're uniform on a support of area sigma, then Fi is equal to 1 over sigma everywhere. Okay? So the smaller the sigma, the smaller the area you can concentrate the distribution on. Right?
We still have to show that this conforms to our other definition of smooth analysis, right?
Well, so let's see. At the moment, I'm proposing this as a different model, or as another definition. So what's nice about this, so what we talked about last time, so for the linear programming results, it was really about Gaussians. So a drawback of that result, a drawback of the linear programming results that we have is we only know how to prove them for Gaussians. And then it's clear what sigma should be. It's the standard deviation of a distribution. So that naturally motivates the question, can we handle lots of distributions? Okay, perturbations, right? So why this obsession with Gaussians? Yes, if you had to pick just one, that'd be a good one. But we'd really like to have it, we'd like to say, any reasonable perturbation works, okay? And so then you have to have some way of parameterizing arbitrary reasonable distributions. And what does every distribution have? Pretty much every reasonable distribution has a density. So why not some parameter on the density? And densities, so sort of saying they're always, at most something is a very natural way to say they're not too spiky. They're not too close to a worst case input. Okay? Certainly if you want, you could take as a special case Fi to be a point plus a Gaussian, truncated so it stays on the square. Okay? That's certainly one instantiation of a distribution Fi. Okay? This says, but it could also be just uniform on some region that has area at least sigma. So in that sense, it's not, again, because of the truncation, it's not identical. But I encourage you to think of the previous case as a special case of this, even though strictly speaking, it's not quite true. Other questions about the perturbation model? So our goal is to show that no matter what distributions over points the adversary picks, conforming to this bound that are not too spiky, local search is fast. Okay? Or again, fast is going to mean polynomial, expected number of iterations in n and in 1 over sigma. Okay. Questions? All right. Andy.
So it's a area 1 square, right? So if you had
Right.
to pick sigma to be like 8 so that stuff couldn't be, you had to limit everything by 1/8, wouldn't that mean that you have to spread out over an area of 8, which is bigger than the square?
Let sigma exceed 1.
Let's see. Yeah, so sigma, you should think of sigma here.
What do they-
Let's see, do I have something flipped?
I don't understand why it can't exceed 1.
Area 1 over sigma, as this goes to 0. Sigma equal 1/8, I think is what you're thinking of.
All right.
Oh, okay, I mean, I guess minimum of this and yeah, right, so how would you, it needs to integrate to 1, right? It's a density, right?
Sure.
So if this is so did you say sigma equal 8 or sigma equal 1/8?
I said sigma equals 8. Because then that probability would be less than 1/8, right?
Yeah, so there's no density on the unit square, which is everywhere at most 1/8. I guess would be my response. Yeah, so right, so sigma is never going to go above 1. Okay, so sigma is going to be between 0 and 1. And we want to be poly in 1 over sigma. Yeah. Other questions? All right. So the proof plan is very clean. Okay, so the rest of this lecture is devoted to a proof of the second part of this theorem. And for the proof plan, it's going to fulfill a promise that I made to you long ago when we were talking about parameterized analysis and its various motivations. So that we're going to bust out parameterized analysis again. So what we're going to do is we're going to just, for any input, we're going to have a parameterized upper bound on the number of iterations of local search in terms of some condition number, in terms of some parameter. Okay, and that's actually going to be easy. Param. So in terms of a condition number. And then the second step is we're going to say that, so only then in the second step do we use the fact that we're doing smooth analysis. And we say, well, because there's this perturbation, the value of the condition number has to be fairly reasonable. Okay, it's not going to be some super nasty version of the condition number. So smooth instance, we're going to show implies that the parameter we identified in part 1 is not too bad. Okay? So that's the plan. And so part 1, usually for smooth analyses, is fairly easy. We talked about this at the end of Wednesday. So in terms of the angle of the polygon after we project the high-dimensional polytope onto the plane, what we said was that what Spielman and Tang really prove is that every angle is bounded away from pi. Okay, and so that bound away from pi can be thought of the condition number. Given that, it was very easy to have this iteration bound of 2 pi over that delta. We're going to have something similar here. Okay? So unlike some of our work in the first couple weeks, this is going to usually be easy. Sometimes understanding in these perturbed instances what's the distribution of this condition number, that can be a technically very challenging problem. It's not too bad today, fortunately, but for some applications it can be quite serious. Okay, so as a thought experiment, let's think about the ramifications when you do a swap like this. Okay, so one of your standard swaps in 2-op. So suppose you swap like in the picture. You used to have the edges uv and xy, and now you replace them with uy and vx. Okay. So this yields a decrease in Tor length, so in objective function value, of, and here's an expression we're going to have to kind of be obsessed with for a lot of the lecture. So I phrase it as the decrease. Okay? So the two edges that we delete, those contribute a positive decrease. And remember, we're using the one norm here. And the two edges that we stick in contribute a negative decrease. Okay? So this is going to be star. Okay? And basically, oh, yeah. And so one thing that's very special about this particular local search application, which is why the main reason I can teach this whole thing in one lecture, is the implications of doing a particular swap, i.e. the change in the objective function value, is totally independent of what's going on in the rest of the tour. Okay? I could care less what order, which points you're going through and in what order here. Same thing here. Doesn't matter. Okay? These contribute the same to the tour before and after. Okay? And these distances are independent of what's up with the rest of the tour. Okay? So at the end, when I talk about challenges and other problems, that'll be a property that breaks down. Okay? That's a really nice property right here. Okay, so very simple expression, depends only on the 4 points u, v, x, y. How does the objective function change when you do this particular swap? All right, so now which swaps are bad? So bad swaps, for our purposes, if we're rooting for local search to be quick, a bad swap, you might think it's one that increases the objective, but actually no. Okay, swaps that increase the objective are never going to fool us into taking them. What we're really nervous about is swaps which decrease the objective, so they're eligible to be taken in local search, but that just barely decrease it at all, make essentially no progress. Okay? So, call a swap epsilon bad if star, so this quantity, is in 0 epsilon. Okay? So remember, this is the decrease in objective function value. So this thing being positive is equivalent to it being an improving move. All right? So a bad swap is one that improves the objective. Star is strictly bigger than 0, but by less than epsilon. Okay? So implicit in this analysis is a condition number, which is equal to the minimum epsilon such that a bad epsilon swap exists. Okay? So basically, we're thinking of an ill-behaved instance as one where there exists these improving local moves that make just very tiny progress. Now, if there are no local moves that make very little progress, if all local moves make rapid progress, then presumably we can only take a few of them before terminating. Okay, because we just improve the objective function so aggressively. All right, so let's prove a more general version of that statement. So here's, this key lemma is going to be what we have to work a little bit to prove. So let me state this, and so to give you some intuition, then I'll show you how this implies the theorem, and then we'll finally go and prove this thing. So here's the key lemma. For all epsilon greater than 0, the probability here is with respect to the input. So remember, we're really doing an average case analysis, sort of, or at least for a fixed choice by the adversary. We're doing average case analysis. So the points are drawn at random. The probability over the points, over the input, that there exists an epsilon bad swap is, at most, epsilon over sigma n to the 4th. Okay? So, don't focus on the end of the 4th at the moment. So again, this probability is over the randomness in the input. The only thing we're really concerned about this right now is this is polynomial. That's eventually going to be good for us. That'll go into iteration bound. 1 over sigma. So remember, 1 over sigma controls how spiky the distribution can be. Okay? So that's 1 over sigma is our upper bound on densities. And so this is just saying the more and more spiky the distributions can get, the probability of a bad swap gets higher and higher and higher. That's okay. And the epsilon is the same thing as this parameter. Okay? So the smaller the epsilon, the less likely you're going to have a swap that's quite that bad. Okay? So the right-hand side should all look pretty reasonable. Now, as far as, so how to think about this and why maybe we'd hope it would be true, although proving it takes a little bit of work. So, it might help to think, instead of this perturbation model, think about the old perturbation model, where an adversary picks a worst case input and then nature kind of just like flicks each point a little bit, right? That's really what we're doing. So suppose you're the adversary and you know that that's what's going to happen, okay? Your points are going to get flicked slightly. And you're trying to create an epsilon bad swap, this swap that decreases things but only by less than epsilon. What seems like a smart strategy for the adversary is you kind of pick your initial points so that you have one or many swaps where if there were no perturbation, this would be a bad swap. Okay, so remember, when you create the initial set of points, you can basically make these swaps be whatever you want, right? So in particular, there is that exponential lower bound instance. Right? So as the adversary, you could pick the points so that with no perturbation, local search would take an exponential number of iterations. Certainly, in that instance, if you think about it, there's got to be a lot of really, really bad swaps, right? If local search takes so long to terminate. Okay? So as an adversary, what you kind of want to do initially is you want to set it up so that you have all these swaps where for a really small epsilon, the swap improvement's like epsilon over 2 or something like that. Now the worry is, things get perturbed, right, afterwards. So if your swap used to be kind of right in the bad regime, in the bad interval of epsilon over 2, and then these points all get, jiggered slightly, there's some chance that either it'll be no longer improving at all, or it'll improve a lot. It'll improve more than epsilon, okay? And intuitively, if you're perturbing things by some density bounded above by 1 over sigma, that kind of, is sort of an amount of force behind the flicks. And you might expect there to be some kind of epsilon over sigma showing up, actually. Right? Because somehow that's sort of the diffusion which is happening in the perturbations. All right? So that's kind of one way to think about this. Like imagine the adversary first set up the points so that this was actually true. And then that's kind of like the worst case for the nature's perturbation. But then, because you have this max 1 over sigma density, there's still only a chance of like epsilon over sigma that it's going to stay in that bad regime. Okay, so let me now show you why, if we can prove the key lemma, we're done. Yeah?
It seems like epsilon's going to have to be n to the -4 or something. Otherwise, that probability is just always going to be 1. Epsilon has to be very small.
Yeah, okay, so all right, so maybe this would help if I let me jump ahead a little bit and point something out. So the points are in the square, right, 0, 1, right? So, and the tor has n edges, right? So every edge is in the unit square, so every edge has constant length at most. So even the worst tor has length O of n in the worst case. And it's going to be at least 0. So if in every single iteration of local search, you make progress, like additive progress, at least 1 over n to the 10th, then at most n to the 11th iterations, you're going to stop. Now that's not a polynomial you're going to brag to anybody about, but it's a polynomial bound. And it really is exponential in the worst case. So you're really getting fundamentally different effects, even if you could prove that. So you're absolutely right, in other words. We want to be thinking of epsilon as very small. Right? So if epsilon is already as big as inverse polynomial, we'll take it. Yeah, good point. So I think more epsilon is more like, 1 over 2 to the root n or something like that. That's what we're really scared of. Yeah. And again, right, for this bad, if you don't have the perturbation, if you just take this worst case exponential instance, exponential number of iterations instance, the average swap has a epsilon inverse exponential, right? Because again, you're going from like n to 0. It took you an exponential number of iterations, so the average improvement is n over 2 to the n. So in that sense, proving that, if we could prove that this probability totally went away once epsilon dropped below 1 over n to the 10, we'd show that the perturbations destroy all of the bad examples. Okay, we'll prove sort of a smooth version of that statement. Yeah. Okay. Any more questions? Yeah.
Can we know or more party swap that doesn't include a poor node swap?
Say it again.
Okay. Well, we couldn't. So if we don't find any nodes or any edges where that we can swap, then have to converge? Is that a converge?
By definition, yeah. So any local search algorithm, you specify the neighborhood. That's a design decision you make at the beginning of
That
specifying.
is up, that is not, or that is a local up, right?
Right, exactly. Right. So this goes back to our discussion about this other gap being between how good is the locally optimal solution versus the globally optimal solution. And in some sense, right, so when you're actually, so when I teach, how do you actually design local search heuristics in 161, right, so one of the main things I talk about is, this trade-off between, the richer your neighborhood, the more time you have to take to search it. On the other hand, hopefully, local minima will be closer to global minima if you have a richer neighborhood. I mean, the extreme neighborhood is every single feasible solution is in your neighborhood. And that, by definition, then turns every local minimum into a global minimum. Of course, now it's not a heuristic. Now you haven't done anything. Okay. So true opt is a relatively small neighborhood as TSP goes. And certainly, if you're trying to do TSP in practice, one does experiment with richer local neighborhoods in order to get closer to the global opt. But for the analysis today, we're just going to focus on the simplest version of the 2-opt case, which, this already itself is used. It's not like this is not useful. This is also useful. Yeah. Okay. So suppose we prove the key lemma. Why are we done? Where we are, here we are. Okay. So we already observed that the worst the initial torque could be is total length 2n. Okay? And most, if you think about it, in the L1 norm, each edge has at most 2. Okay? So 2n could be the worst. 0 obviously is the best. So if we have no epsilon bad swaps, and this is sort of our very easy parameterized analysis, then local search terminates in at most 2n over epsilon iterations. Agreed? If there's no epsilon bad swaps, every swap that improves by epsilon. You start at 2n, you go to 0. So that's it. Okay? So we're golden if epsilon is inverse poly. Okay? All right, so let's figure out how long it's going to take now, assuming we've proved the key lemma. And again, because each iteration can be implemented in polynomial time, this just boils down to analyzing the expected number of iterations. Okay, so we want to prove this is polynomial in n and 1 over sigma. So first, just by the definition of expectation, we sum over all of the values that I'm going to use capital M as the random variable denoting the number of iterations, which is random, again, over the input. And actually, let me rewrite this. So M is a non-negative integer valued variable. So another way I can write this sum is I just sum up all of the probabilities that the random variable is at least something. Okay. So the only thing I'm using here now is that the random variable is non-negative and integer valued. Some of you, I'm sure, have seen this before. If you've never seen it or you forgot it, the best thing to do is just stare at it for 60 seconds, and then you'll realize it's, once you see it, you'll be like, oh yes, that's obvious. And so, oh no, don't do that. Okay. All right, so now, why did I rewrite it this way? I rewrote it this way because the only way that the number of iterations can exceed m is if we have a pretty bad swap, okay? With epsilon equal to 2n over m. All right, that's by this, right? So if every swap, if there was no bad swap with parameter value 2n over capital M, then we're certainly not going to require m or more iterations, all right? So a necessary condition for this, and therefore an only bigger probability, is to sum up the probabilities of bad swaps. So there exists a 2n over m bad swap. Okay? All right. So now we use the key lemma, right? So we're invoking the key lemma with epsilon equal to 2n over m, over capital M. All right? So the little n on the top, we'll just sort of add that to the exponent. That'll become an n to the 5th. The epsilon goes away. There's a sigma on the bottom. There's an m on the bottom. Okay? So key lemma. So let's pull out everything that doesn't depend on capital M, namely n to the 5th over sigma, sum m at least 1 over m. Okay? Now at first this kind of looks like a bummer because this thing diverges, right? On the other hand, like how big could m be? If you thought about it, we actually discussed in passing a finite upper bound on capital M. How many iterations could local search take to terminate? Could it really take infinite? Could it take forever and ever and ever? No. It strictly improves the objective function value, and there's only n factorial tors. Okay? So we only need to sum this thing up to n factorial. Okay?
Wow, this is okay.
So this is well approximated by the natural logarithm, right? The harmonic sum. So natural log of n factorial, which by, if you like, Stirling's approximation, theta n log n, giving us an upper bound of sigma to the minus 1, n to the 6th log n. Okay. So that's why if we prove the key lemma, then we're done. Right? It's just proving a sufficiently rapidly decreasing probability bound on the probability of a bad swap. Okay? Yeah. So any questions? Okay. So a couple comments before we start on the key lemma. One can improve this upper bound, and actually the same Englert et al. Paper do prove a bound where this n to the 6th becomes n to the 4th. The way they do that, they use the exact same kind of high-level framework. They prove an upgraded version of the key lemma. And what they do is rather than considering single swaps, they consider pairs of swaps. So the key lemma is basically saying, you know, if you just take an arbitrary such swap, it lower bounds the progress you'll make with one swap. So instead they prove a key lemma where they say, well, look at two swaps on a row. One of them might be bad, but one of the two will be good. And if you think about it, that gives you exactly the same iteration bound up to a factor of 2. Okay, so they prove a better lower bound on the rate of progress you make if you break the iterations into pairs. You do have to work a lot harder to prove that, I have to say. Okay, so but with a lot more work, you can get this down to n to the 4th. There's still a gap between that n to the 4th and what seems to be the empirical performance, which is more like n squared or even a little bit better. But this seems to be the deal with smooth analysis. Okay, so it does let you turn exponentials into polynomials, but it just seems to get tight bounds. The amount of analytical work required is just overwhelming. Okay, so it really just doesn't seem like a framework that allows us to nail the exponent of the polynomial. Okay? But we're here to celebrate its good points, so not complain. All right, so on to the proof of the key lemma, unless there's any questions before that. All right. All right, so consider a fixed swap. So how many different kinds of swaps, how many different swaps do we have to consider? So a swap is like this. So how many free parameters do we have in star here?
Which is 4.
Yeah. So we have degrees of freedom for u, v, x, and y. Okay? So that gives us n to the 4th possible swaps we have to consider. Again, very happily, star is independent about what's going on with the rest of the points. Okay? So consider a fixed swap. We're going to show that the probability for this fixed swap, that star is in 0 epsilon, is big O of epsilon over sigma. Okay? Having done this, we can apply the union bound over the end of the fourth different swaps, and that gives us the claimed bound. Okay? So that's really nice. It just boils down to analyzing one swap. Okay? That's what makes this a nice analysis. So end of the fourth swaps done by union bound. Okay. Now, let me expand this. Let's see, U1 minus V1 plus X1 minus Y1. So in terms of the coordinates, so we have these 4 absolute values from the first coordinate plus exactly the same thing with all of the subscript 1s replaced by subscript 2s. Okay? So this is what we're trying to analyze, right? So the key lemma is all about trying to get a handle on the distribution of this number. Okay? Now the reason I've expanded out the norms is because I'm just trying to, so we'll be able to do this, it'll be pretty straightforward. But the one thing which is kind of annoying and forces us to work a little bit harder than we might otherwise is all these absolute values. Okay? So if we picked some other norm, there'd be some other irritation. Like the Euclidean norm, we'd have some square root and some squares, right? So we'd deal with it, there'd be some other way of dealing with it. But it's something we got to deal with, okay? So we have these absolute values. So I guess now I can erase this. So here's the way we're going to deal with this, okay? So let's say trick. So we want to say this thing is only between 0 and epsilon with low probability. We're going to say, well, it would be a lot easier to deal with if we knew which of these coordinates was bigger than the other one, right? So right now, this is either u1 minus v1 or v1 minus u1, and it depends on which of them is bigger, okay? So let's sort of just guess the sign of each of these absolute values, okay? So here's what I mean. So for a fixed ordering of the 4 values in the first coordinate, okay, so in ordering, I just mean which of these is biggest, second biggest, third biggest, fourth biggest. Okay, so there's 4 factorial choices for orderings. I guess I'm ignoring ties. That would be a few more. 4 factorial choices here. Okay, so 4 factorial squared choices I'm making. Now, once you tell me which of these is bigger than the other, this expression simplifies. Okay, this expression is then just some linear combination in these 8 values. Right? So once I fix the ordering, each of these absolute values either just becomes a times 1 or a times minus 1. Okay? So I just get this linear combination in terms of these 8 variables. Also, because all coefficients in these terms are 1, when I look at the linear combination that I get, every coefficient of a variable is an integer, possibly 0, but it's an integer. Right? So I'm going to get either like 2 times u1, or minus 2 times u1, or maybe 0 times u1. Okay? All right. So the expression star, the thing that we want to show, is very unlikely to be between 0 and epsilon. Once we've made these 4 factorial squared choices, boils down to a linear combination of 8 variables with integer coefficients. Okay? And now here's a sort of trivial but also sort of subtle point. So the expression that we care about, okay, the sum of all of these absolute values of differences, this lies in the interval 0 epsilon only if one of these 24 squared linear combos lies in 0 epsilon. Okay? So let me make sure it's clear what I'm doing. This is star. This is the only number we actually care about. Okay? If you substitute values for the 8 variables, you get a real number. Okay? So for some instantiations of those 8 variables, you're going to get something between 0 and epsilon. For some, you won't. On this board, so this is just one expression. On this board, I've written more like ballpark 5,000 expressions. Okay? 24 squared, or 500 expressions. Okay? Yeah. All right, 500 expressions. All right? No matter what, the value on the left board is equal to at least one of the 500 expressions on this board. Okay? Which one depends on the relative ordering of all of these pairs. Okay? But I've written out these 500 expressions that have covered every single case of what this thing might evaluate to. Okay? So if I instantiate these 8 variables so that this thing winds up being between 0 and epsilon, and I look at these 500 instantiations with those exact same variable values, one of those is between 0 and epsilon. In particular, the one of these, which is equal to this one. All right? Why am I doing this? Rather than upper bounding the probability that this thing's between 0 and epsilon, why don't I instead just upper bound the probability that any one of these 500 things is between 0 and epsilon? Okay, that's a looser condition. I get an upper bound on the probability. Is it clear what I'm doing? Okay. It's kind of a hack, frankly. Okay. But we can get away with it because, 500 is a constant. So. I mean, there's slicker ways you could do this if you wanted. But, just as far as convincing yourself all this stuff is true, this is probably the easiest way to do it. So any questions about that? About this note? A necessary condition for this thing to be bad, for this thing to be between 0 and epsilon, is that one of these 500 combinations, one of these 500 linear combinations is between 0 and epsilon. Necessary condition. Okay. All right. Good. So claim. So pick your favorite linear combination in the middle board. We'll just take a union bound over all 500 of them. The probability that a linear combo of your choosing is between 0 and epsilon is at most sigma over delta. Okay? And so then the union bound gives us a 500 times sigma over delta, which is kosher by this claim. Okay. So why is this true? Let's prove the claim. Well, we can certainly assume that one of the coefficients is non-zero. Okay, so again, remember, linear combination in 8 variables. U1, V1, X1, Y1, U2, V2, X2, Y2. Okay, that's what's linear. So it's those 8 variables, each with a coefficient. If all of those coefficients are 0, then this linear combination is always 0. So it's not going to be strictly between 0 and epsilon. So we can assume one of the coefficients is not 0. All right. So now we use the principle of deferred decisions. Oh yeah. So let's say Z. Okay, so Z is one of these 8 variables that has a non-zero coefficient. So now we use the principle of deferred decisions. Right, so we're going to prove an even stronger statement that this probability is at most epsilon over sigma, actually no matter how you condition on the values of the other 7 variables. So condition on the values of all other 7 variables. Okay, so don't forget what's random. Okay, remember the adversary has supplied these distributions from which the values of these 8 variables are drawn. So I'm saying draw them for the 7 other than z. Z remains random. Okay? Maybe it'll also help to just remember, like, what's the intuition for what we're trying to prove? Think of this adversary who initially picked this really bad instance and now nature's flicking it. Okay? Basically what I'm saying here is, even if I just get to flick one of the points, that's good enough to prove that, your devious swap you had in mind is actually either going to not be improving or improve more than epsilon. All right? So only z remains being random. That's going to be enough. Okay? All right, so condition on values of all other 7 variables. Good. Now, so since the coefficient of z, all right, let's put it this way. Okay, so residual expression after conditioning has the form lambda for some number, some real number, plus alpha times z, where alpha here is an integer and not equal to 0. Okay? Remember, the only thing that remains that's random is z. The other 7 variables have been instantiated, so we just have something like 5 plus 2 times z. So and we're worried about what's the probability this thing lies in the interval 0 epsilon. Okay? Well, intuitively, the worst case is where the value of lambda is like epsilon over 2. Right? So even before we instantiate z, it's sort of like centered right in the bad interval. On the other hand, we know that z, by assumption, comes from a pretty diffuse distribution. The density is at most 1 over sigma everywhere. Okay? So in other words, in an area of like merely epsilon, you can only fit in a small amount of density. Okay? It just can't be that likely it's going to be in this very tiny region. Okay? Because it's not too spiky. Okay? Now the only worry would be that, okay, well maybe z is really diffuse, but then maybe alpha is concentrating it. Okay? But alpha is an integer. Okay, so it has magnitude at least 1. So it's actually only spreading z even more diffusely. Okay? So alpha z is only less spiky than z. Okay? Because alpha is an integer. So you put all that together. So density of z is at most 1 over sigma everywhere. So probability that lambda plus alpha z is in 0 epsilon is at most the length of the interval over the density times the density upper bound, 1 over sigma. Okay, which is what we wanted to prove. Okay. And this is also, this is a simple but still very characteristic type of smooth analysis. This sort of mixture of sort of principle of deferred decisions and then still having residual randomness, which is just sufficient to prove that some condition number is large. Okay, many of them have this flavor. Okay? And I like this proof in particular because I think those ingredients shine through in the most transparent way. Any questions? Yeah.
So it seems like a more aggressive proof of that probability would be one way to eliminate some of sort of the slack between theory and
Of which probability?
sort of the probability down what you just showed here.
Which part of it?
Well, I guess
The claim or
Well,
the factor 500 or?
yeah, like the deferred decisions, sort of this blow up, right?
Yeah, true. But let me point out that, so all of the blow up we're suffering here is suppressed by the big O notation anyways.
Okay.
Right, so, so the real upper bound is, something like 500 times n to the 6th, whereas the practical performance might be, 1 times n to the 1.5. So you might be able to bring down the leading coefficient, but none of this will help you bring down the exponent. And even with a lot of hard work, people don't know how to get past n to the 4th. So getting n to the 4th to n to the 3rd, it may be as simple as something, as conceptually simple as something as looking at not just pairs of swaps, but even longer chains of swaps. But pairs of swaps are already, a real challenge to understand how to leverage those to get you a better upper bound. So my belief would be it is probably possible in principle to prove a smooth analysis bound which starts approaching what people see in practice. Maybe not exactly, but I do believe you could beat n to the fourth, for example. But it's not clear that the amount of work it would require is justified, really, for anybody to do. So,
Specifically about the end of the fourth swaps.
yeah.
Why are we getting that when we only have like O of n? We have n edges that we have to choose from, right?
Right. So good question. So if I give you a tour, if you have a tour that you're working with, and you know that the swap you're going to take right now is a neighboring one of this tour, then you're right. Then it's only n choose 2 edges. So that's n squared. So from any given tour, there's n squared directions you could go. But if you think about every tour you might find yourself in at some part of local search, now all of a sudden, the number of different swaps you might see are literally the number of edges in the entire graph, n squared choose 2. So that's the difference.
And where this is a bound over the entire algorithm's execution.
Yeah, because you don't know where it starts, you don't know where it's ever going to be. I mean, literally every swap might have an opportunity to be executed at some point in local search. It seems very hard to a priori rule out any particular swap coming up.
Cool.
Yeah.
Thanks.
Yep. Any other questions? Yep.
I can see how the lambda plus alpha z holds for the specific variable that is not equal to 0.
Right.
But why doesn't it need to hold for every variable?
So the sneaky thing that I did is I first, intuitively, I let you choose the linear combination first. Then I look at which variable has a non-zero coefficient. If none of them have a non-zero coefficient, I'm done.
Yeah, that's
Okay, but then you pick the linear combination, I pick the thing with a non-zero coefficient, and now I use that to decide how to apply the principle of deferred decisions. And I'm going to condition, i.e. substitute values for, 7 of the variables other than the one that has a non-zero coefficient. So I'm basically adaptively picking which 7 variables, right, so I'm adaptively picking which variable to save for the last, based on the linear combination. So, in fact, I had a bug in an earlier version of this lecture because missing that subtlety. So it's sort of a subtle point. So you basically adaptively apply the principle of deferred decisions differently for different linear combinations. Yeah. But for any linear combination, there's one that works, and that's all we need. So, other questions? Okay. Then, one other comment. So one thing I'll ask you to do on homework is notice that all this stuff goes through even if you're not in the plane. Okay, so you have points in a higher dimensional space, but say with a constant dimensional space, 3 space, 4 space, whatever, you can push all this analysis through and you still get the exact same iteration count. The dependence on D shows up only in the suppressed constant in the big O notation. Okay? And as I said earlier, and these I won't make you do, but you can do similar results for Euclidean norm and other norms if you want. Okay, so I presented the easiest one to present, but the results are more general. Okay, so let me conclude with just some open questions and speculations. Because again, I mean, if you think about what are the ingredients that seem to make, problems well suited to local search, to smooth analysis, local search just ticks all the boxes. You have these brittle, exponential lower bounds. It's essentially about running time and so on. We have successes like this, but there's a lot of local search algorithms that we don't know whether or not they have smooth complexity or not. All right, so the first thing would be just to identify, right, so people use local search for all kinds of different computational problems. And at least for sort of the most fundamental ones, it would be nice to show that local search has polynomial smooth complexity. Okay, so let's just say more polysmoothed bounds for local search. So So there are a few others. I don't want to give you the sense that TSP is the only one people have done successfully. There's other examples as well. K-means is one where actually done by graduate students here at Stanford last decade, or at least the initial results were. David Arthur and Sergei Vasilevsky. So that's a really nice example of an actually pretty hard local search algorithm that was proven to have smooth polynomial time. As a challenge problem, let me mention max cut. So this is the problem where you're given an undirected graph with edge weights, and you want to split it into two parts, maximizing the weight of the edges crossing the cut. Okay, so unlike minimum cut, which is polynomial time solvable, maximum cut is NP hard. Okay, and local search is one way you can approach it. On the homework, I'll ask you to show that if the graph has bounded degree, okay, so all degrees are at most constant, then in fact local search, oh right, I should say what the local search algorithm is. Here it's really simple. You just check if moving a vertex from A to B helps, similarly from B to A. If any of these flips, it's called the flip neighborhood, if any single vertex move improves the objective, increases the weight of the crossing edges, do it. Stop when there's no more such moves. So I'll ask you to prove that that local search algorithm has polynomial smooth complexity in bounded degree graphs. Okay? The analysis of that has much of the same flavor of this TSP analysis, I would say. Again, sort of the moral reason why we know how to analyze this is because, you know, like in TSP, in some sense there are only an n to the 4, a polynomial number of different things that could happen. In bounded degree graphs, if you think about it in the right way, you recognize there's only a polynomial number of different relevant events as far as the different swaps that could happen. What's open is general graphs. Okay, so we don't know whether or not local search has polynomial smooth complexity in general graphs. Just as of January of this year, so maybe 10 months ago or so, we learned that it does at least have sub-exponential running time, smooth complexity. Okay, so a so-called quasi-polynomial time bound was proven. That means n raised to the log n, or if you prefer 2 to the log squared n. Okay, that's a lot better than 2 to the n, but it's not polynomial. Okay, it's super polynomial. Generally, you know, people rarely believe that a quasi-polynomial bound is the right answer. People usually think it's either polynomial or exponential. There are exceptions, but it's a rule of thumb. So people sort of expect that the right answer there is polynomial, but no one knows how to prove it. Okay? So that's sort of a concrete question which we don't specifically know. Frankly, I actually think much more sweeping positive results should be true. So I actually think pretty much every single local search problem should have polynomial smooth complexity, and it's just a matter of proving it. So believe it or not, there's actually a definition of pretty much all local search problems. There's a complexity class called PLS. This is by Johnson, Papadimitriou, and Yannakakis. It stands for polynomial local search, and this is in some sense the analog of NP, but for local search problems. And I'll put a link on the website. I actually teach a lecture on this in my algorithmic game theory class, so I'll post some lecture notes if you want to read more, sort of a gentle introduction to this complexity class. And so I think all these local search problems should be solvable in polynomial smooth complexity. Okay, and I have various reasons for believing that. Could be wrong, of course, but I think it's more an issue of proving it than it being true. I think that's more the obstacle. There's two versions, actually, of this conjecture, if you want to call it that. The stronger one I'm less sure about. Okay, so the stronger statement would just say generic local search, as we've discussed. Okay, meaning you just follow your nose. If there's multiple improving moves, take any of them arbitrarily. The generic local search always has smooth polynomial complexity. That would be a strong statement. Still might be true. A weaker statement would be, well, I don't know about generic local search, but I can at least craft some optimized, smarter algorithm which is guaranteed to compute a locally minimum solution in smooth polynomial time. Okay? So I'm not going to restrict myself to this generic local search algorithm. I'm going to do something smarter. Now you might ask, what on earth else could you do other than generic local search in a generic local search problem? But there are some tricks you can do. So first of all, you could say, well, let's just focus on the moves that improve the most. So not an arbitrary improving move, but when there are many, you could have some smart way of distinguishing between them. There's other tricks, like you can do things like round the objective function, discretize the objective function, sort of to smooth out some jagged edges of the search surface. Okay, so that, I don't know, I think it might be really hard to prove, but I think actually that might be true. It'd be really cool. It'd be a very sweeping positive statement. In 2 lectures, so a week from today, I'll show you an analogous result that also has the same flavor of generality, sweeping positive results, which says that for all problems which emit a pseudo-polynomial time algorithm, all of them have smooth polynomial complexity, again, by carefully crafting an algorithm to solve it. So that's another analogy I have in mind in thinking that this might be true. Question?
Is generic local search, I mean, why do we even know that it converges in like the general case? I mean, couldn't there be cycles?
No, because it's defined to only improve the objective function value.
Okay, yeah, I guess.
Yeah, it's a good question. But so, I mean, and this is sort of the subtleties of what does it mean for a problem to be in PLS. And so some of the necessary conditions to be in PLS is you have to have an objective function value which can be evaluated in polynomial time. And then you also have to be operating on, so basically the feasible solutions have to have a polynomial size description. So there's only an exponential number of possible feasible solutions. They can't grow in length, so there's not going to be an infinite number of feasible solutions. So by definition, if you look at the fine print of this complexity class, local search is guaranteed to terminate in exponential time on every single problem. Yeah. Other questions? On Wednesday, we'll talk about Pareto curves. See you then.